Welcome back, focused learners. Okay, so today on The Explainer, we are doing a step-by-step teardown of an absolutely massive concept. We're looking at how small factories and emerging enterprises can completely unlock advanced manufacturing tracking, but without that exorbitant price tag. We're talking about building a custom, low-cost manufacturing execution system, or MES, literally from the ground up. Get ready, because we are going to demystify the tech and show you exactly how it's done.
But to really understand the solution, we first have to talk about the massive capital barrier keeping small to medium enterprises locked out of digital maturity. Implementing a commercial MES often demands a heavy upfront investment, starting at $20,000 or more. Now, for a massive corporate plant, sure, that's a drop in the bucket. But for a smaller operation trying to track their production, that price tag alone stops digital transformation dead in its tracks.
Okay, let's dive into the blueprint for today's explainer. First, the Industry 4.0 barrier. Second, our open source hero. Third, the Purdue architecture. Fourth, the digital handshake. Fifth, securing the factory. And finally, full traceability achieved.
All right, kicking things off with Section 1, the Industry 4.0 barrier, the high cost of entry. So, according to a 2024 Unibo source, scale really shouldn't hold you back from digital maturity. But it often does, right? You've got these commercial software models demanding heavy upfront capital and those painful recurring licensing fees. But consider the alternative. A modular, $0 licensing approach. You're just paying for hardware to get real-time visibility and enterprise-grade data integrity. I mean, why rent the software when you can build the bridge yourself?
Moving right along to Section 2, the open source hero, Python on the shop floor.
So how do we bypass those massive software fees? Well, meet the hero of our story, a custom Python open source core. The code running behind the scenes here is just brilliantly elegant. Uses a library called PyCom3, which basically lets it speak the native language of the Logix processors right there on the shop floor. No translators needed. And because it uses threading, the user interface remains completely non-blocking while it seamlessly scans the floor tags. The best part? For the maintenance techs out there, this whole script gets compiled into one single, zero-dependency executable file. You literally just drop it onto a shop floor PC, double-click, and boom, it gets to work.
Now, you might be thinking cheap means weak, right? Actually, scratch that. It is definitely not the case here. This baseline architecture is completely scalable. You have the total freedom to modify both the programmable logic controller, the PLC, and the Python code to capture the exact metrics your operation actually cares about. Whether you need to track precise cycle times for overall equipment effectiveness or document those frustrating micro-stops, defects, and scrap rates that normally go totally unrecorded, the power is entirely in your hands. It's all about capturing the nuances of your unique operation.
Which brings us to Section 3, the Purdue architecture, structuring data flows.
Okay, so we have our software, but where does it actually live in the physical factory? Think of it like a ladder based on the ISA 95 framework, commonly known as the Purdue model. Down at the very bottom, levels 0 and 1 represent the physical production and control level. Your CompactLogix PLCs are down there doing the heavy lifting, sensing, manipulating, keeping machines safe in real time. Now, climb up that ladder to level 3. This is the manufacturing operations planning level, and ta-da, that is exactly where our industrial PC sits running our Python service. It aggregates all that raw data from below, acting as the perfect bridge before handing it off to level 4, the management and business logistics tier.
Let's jump to Section 4, the digital handshake, flawless execution.
Let's zoom way in for a second. How do we actually capture this data in real time without dropping or duplicating a single piece? It all starts with the PLC trigger. The exact millisecond a machine finishes a production cycle, the local PLC grabs that vital production data, the part number, the serial number, the cycle time. Then it fires a lightning-fast trigger. It just toggles a specific bit called MES_part_OK from a 0 to a 1.
Instantly, our Python service spots that high bit. It swoops in, reads the CIP data packet, securely logs it straight to a local CSV file, and then completes the handshake. How? By writing a 0 right back to that exact same trigger bit. It's essentially a simple, foolproof digital receipt. It tells the PLC, hey, I've got it, you are officially clear to reset the buffer for the next unit.
Let's just quickly summarize that crucial sequence, because it truly is the heartbeat of the whole system. 1. The PLC trigger fires, setting the OK bit to 1. 2. The Python pulse reads the data and logs it. 3. Python sends an EK
acknowledging and clearing the buffer by writing the 0. That strict 1-2-3 chronological flow ensures flawless execution. You will never double count apart, and you will absolutely never miss a cycle. It's perfectly synchronized.
Next up, Section 5, Securing the Factory, the OT/IT Shield. Now, with data flowing so freely between the machines and our Python script, how do we keep this delicate handshake safe from outside network interference? The absolutely crucial point here is building an OT/IT shield, separating operational technology from information technology. Imagine someone in the front office downloading a massive file and suddenly lagging out your critical manufacturing data. Total nightmare, right? To prevent this, we isolate the PLCs on a dedicated machine VLAN, like a 192.168.1.x subnet. Then, a NAT router translates that local IP to the plant network. Throw in some strict firewall rules that only allow specific CIP traffic through, and boom, you've blocked office network interference while keeping the underlying machine logic heavily protected and secure.
And finally, Section 6, Full Traceability Achieved, from floor to cloud.
Okay, it's time for the grand finale. Let's pull it all together. The code, the Purdue framework, that slick digital handshake, and the network shield, and see how this builds into an advanced IoT assembly line. Imagine a part rolling through Station 1. The local PLC captures the serial number and cycle time, executes that flawless digital handshake with the Python service, and securely passes that data right through our NAT router. That data then flows up the Purdue ladder to level 4, materializing instantly on a real-time Google Cloud data dashboard. So now, management can be sitting anywhere in the world, securely looking at live pie charts, efficiency metrics, and full unit traceability. It's like having the pulse of your factory right at your fingertips.
So, what does this all mean for you? We've just seen how open-source tools like Python and PyCom3 can completely dismantle the massive financial barriers of Industry 4.0. If enterprise-grade data integrity and full shop-floor-to-cloud traceability can be achieved for practically just the cost of the hardware, what is stopping your factory from building its own data journey today? The tools are literally right there, and the blueprint is ready. Thank you so much for joining me on this explainer. Keep learning, and I'll see you in the next one.